let us elaborate more on the properties of the area function. So, as a brief reminder, what this function does, it solves the following equation. And in all our previous consideration, we have considered this function on the real axis. And now we will be interested in its properties in the entire complex plane. And in order to study it, we need to perform analytical continuation, which in this case is relatively straightforward. And we will define area function in the complex plane by the following integral, with contour to be specified in a moment. And it's straightforward to check that this integral does indeed solve area's equation. And what we need to require is for the contour to go to infinity in such domains that the exponential decays. So in order to specify these domains, let us first draw the complex plane of T. And in this complex plane, we need to choose such sectors that a real part of T cube is negative. Is position of the following lines. And it happens that the choice of the contour which corresponds to area function as we got used to know it corresponds to the contour which goes to infinity in that defined sectors. So any contour which has ends which go to infinity in the dashed sectors leads upon the integration to the area function which we are well familiar. But this definition allows for analytical continuation in the entire complex plane of Z. So let us now think a bit on the properties of this function. So what we know from previous consideration and this area function by definition does solve this area equation and has the following properties. So it defines a function which decays exponentially at large positive x. So now we are talking about real Z, and has oscillatory type decay at negative x, which corresponds to real Z. But now we're interested in how does this function behave at complex Z. And in order to understand this, we are going to study this integral by the saddle point technique. And as usual, the first step in this study is to find saddle points of the exponential. So in our case, expression in the exponential is t cube over 3 minus tz. So let us find the saddle points. And the equation for the saddle points f prime equal to 0 becomes t squared equal z. And now recall that z can be arbitrary complex number. Let us solve this equation in the following form. And in principle, if we are looking at the complex plane of T, where the integration is performed, we understand that, for example, if Z is real and positive, then the stationary points are located at the real axis of T. And with change of the argument of Z, these saddle points rotate in the position of the saddle points rotates in the complex plane. And for example, if Z is negative and real, this corresponds to that domain of area function on the real axis, then, for example, the saddle points come exactly at the imaginary axis. So, and already at this level, we see that what happens with this integral representation is, first of all, the contour, of course, remains the same as it defined with respect to decay of the exponential. But what changes when we change the argument of Z, that is the direction in the complex plane where we go to infinity, is the rotation of the saddle points in the complex plane of T. And it happens that this rotation has a profound effect on the configuration of the saddle path and on the asymptotic properties of the area function in the complex plane, as we will discuss momentarily. Before we go into details of behavior of this function in the entire complex plane, let us recall briefly what happens at positive z. Then there are two saddle points, and the original integration path goes somehow like that. And of course, we may deform it to a certain extent, as long as the integral remains convergent. So our first step in consideration of this integral is to understand what is the topology of the steepest descent paths. So to each of the saddle points, there is a certain steepest descent path attached. So how is it defined? As usual, this function in the exponential, which we will call f of t from now on, defines a certain curve in the complex plane according to the following equation. So let us recall briefly why this curve is of much importance. So mainly because of the fact that this expression in general is a quickly oscillating function of t, which belongs to the integration path. And as long as the imaginary path of the exponential remains constant, of course it means that the oscillations effectively disappear. So now we have to understand how actually do we deform our integration contour, and how is it possible to deform it in such a way that the integral, first of all, remains convergent, and second, passes through some of the saddle points. So in order to resolve this, let us first understand how the steepest descent path attached to each of the saddle points look like. In order to achieve this, we need to solve this equation explicitly. We don't often need to do this, but for now it will be very instructive. So let us write t equal x plus iy. That is what we have just done, is separated explicitly a real and imaginary part of t, and substituted to the expression in the exponential, and we'll, for a second we will assume that z is real. So what happens with f of t is the following. This f of t becomes x plus iy cubed minus z x plus I. Let us now evaluate the imaginary part of this expression. So let us first write it a bit more explicitly. This is nothing but imaginary part of f of t, and we need to find a curve in the complex plane such that imaginary part of f of t coincides with its value on the saddle point. And since the saddle point is on the real axis now, then imaginary part of f of t at this point is exactly 0. So the equation which we need to solve is the following. This one is relatively simple, and the easiest way to look at it is to realize that, first of all, there is one solution to this equation with y identically equal to 0. This will be the curve which goes like that. So one of the solutions to this equation is a curve which goes along the real axis. So let us look for another solutions, and in order to find them, we will just cancel out this y, so that equation becomes x squared minus y squared over 3 minus z equal to 0. And this one can be easily solved for anything you wish, for, say, for x. And x equals plus minus square root of z plus y squared over 3. And we can easily draw these curves on the complex plane. And they go like this. They pass, each of them plus or minus passes through the corresponding saddle point. And one of them goes like this. And another goes like this. And again, recall that what we are trying to achieve is we're trying to deform our original integration path in such a way that its ends belong to the regions of the convergence, and it passes through some of the, or possibly all, saddle points. So in this case, let us try to understand what deformations are possible. So of course, it's obvious that our original integration path can be very well deformed into this new contour, which just corresponds to the curve given by this equation with sign plus. So here, a natural question can arise. Can we somehow deform this contour in such a way that both of the saddle points will be on this contour, and at the same time remain on the surfaces of the constant phase. And in fact, in this situation, geometrically it's impossible, because imagine you are trying to start from this convergence region. Then in principle you may reach this saddle point, and then you can imagine that you go across this y equals 0 surface. Then you reach this point, but afterwards there is no way that you can turn back to the convergence regions. So it means that in this situation, when z is real and positive, the only way to deform original integration contour, to first of all pass through the saddle points, and second to go along the stationary phase surfaces, is like that. And after this deformation, the integral becomes such that it is dominated by the immediate vicinity of the saddle point. In fact, it can be calculated by the saddle point technique by expansion in the vicinity of this point. This will be one of your exercises to this lecture, and in doing this you will recover the asymptotic of the area function from textbook. But for now, let us try to understand what happens with this logic when the variable z goes off the real axis and acquires finite imaginary path. So we have just figured out that our integral representation for the area function has indeed correct behavior at large and positive z. Correct in a sense that it does reproduce what we expect from the area function, that is exponential decay at large real values of the argument. And this was achieved because we found that due to the structure of the integral, at large and positive values of argument, the proper contour passes only through one of the saddle points. Let us now think for a second and try to reconcile what we have achieved with what we expect and what we know about area function. We know that this function, what it does actually is at negative values of the argument, it is real first of all, and then it has oscillations. What do we understand from this geometrical picture? How should it be reconciled with this asymptotic? We know that this exponential decay is very well consistent with only one saddle point contributing to the exponential. But from the other side, the function being oscillating means that such oscillation together with real valuedness of the function is possible only when both of the saddle points contribute to the integral. And in fact, indeed, from what we have discussed previously, we understand that when z is real and negative, two saddle points plus and minus square root of z belong to the imaginary axis, and the domains of integration are as before, and it is indeed possible to pass across each of the saddle points and end up with the contour in the allowed domains. So here comes some interesting question. Now imagine this used to be complex planes of integration variable t, but now let us recall what we are actually looking for. In principle, we discuss properties of the function a of z for various values complex of the argument z, and we understand that somewhere here on the real and positive part of the z-axis we have exponential decay and only one saddle point contributing, and somewhere here at negative and real values of z, we understand that we have, in order to be consistent with our general expectation, we need to have a contour which passes through both of the saddle points. So we understand that, in other words, that somewhere here only one saddle point lies on the proper integration contour, and somewhere here both of them should lie on the proper integration contour. But now imagine for a second that you are now not on the real axis, positive or negative, but instead you change your z and it acquires some imaginary path. In the end, we want to make the whole road from positive semi-axis to negative semi-axis, but it will be very instructive to follow the fate of these two pictures when z starts to move into the complex plane. So it's clear that depending on the value of z, the position of the saddle points will vary. And in fact, we know that when z changes from positive to negative, this couple of saddle points turns to this couple of saddle points. And it's very interesting to understand what happens in between. And indeed, we understand that when z changes its argument and goes like this, ending up at negative semi-axis, of course, this 1 should at some point change into 2. And this means that if we study the asymptotics of area function in the entire complex plane, this asymptotic should at some argument of the independent value change rather drastically. And this phenomenon is called Stokes phenomena. And we will now understand what does it matter, what does it mean from the point of view of the position of the saddle points and topology of the saddle point contour, and how actually we can evaluate the asymptotics of the area function in the various sectors of the complex plane. And in order to proceed, let us briefly summarize the procedure again, the general logics of this procedure. So the integral representation, which we are dealing with, is of the following form, where f of t is t cubed over t over 3 minus zt, and the integration contour is such that it ends up in this now shadowed domains. And we need to apply our saddle point technique for study of this integral. And please, again, note that this can be to a certain extent non-trivial, because we understand that when z is real and positive, only one saddle point contributes. When z is real and negative, both of them contribute. And now we need to understand where exactly does the change in this behavior happen.